Good morning, good afternoon, good evening, whenever and wherever you are. My name is Anna Rochelle, and we are in Algebra 1, Chapter 6, Lesson 5, Solving Exponential Equations. Some of these are a little bit more basic than others, and some of them require graphing calculators. Some of them require, knowing your perfect squares and perfect cubes and perfect whatever, fourth, fifth, sixth exponential power. Um, so we're going to get started. These are problems sent in by a student. Um, and there's 22 problems in total. My recommendation is when you're going through this video, if you were, for example, absent on class day when you learned this chapter, I would recommend listening to maybe one or two, trying the next one or two, watching the video so that you can see the answers and make sure that you are actually getting the right answers. Okay, so without further ado, the idea is when you have the same base, whoopsie daisy, that was the wrong thing. I did not want to do that. This is what I want to do. Okay. So when you have the same base, we can essentially remove the base and just compare the exponents. Eventually in Algebra 2, you'll learn another method to be able to compare these numbers. But for right now, all we're doing is we're understanding that if the base is the same, we can go in and compare the exponents. And then this just becomes a single step equation from course one math, where you divide by 4. So x is 3. Same business here. We've got the same exponents. So we're going to go in and we're going to compare x plus 5 and 20. So we're going to subtract 5 on both sides, and we're going to get x is 15. Some teachers may say you need to check the work. I would recommend checking it if it's a little bit more intense than just these kinds of problems. Okay, so again, we have the same base. We want to take a look at our exponents. So I'm going to subtract 4x from both sides. I'm going to end up with negative 5 equals negative 2x. Divide by negative 2, x is 5 over 2. And honestly, we could leave it improper, no problem. Okay, so same base again. We've got 6x minus 3 equals negative 3 plus 4x. I know that I can add 3 to both sides, so that'll cancel both of them. And then I've got 6x is 4x. I'm going to subtract 4x from both sides. That'll cancel. I'll end up with 2x is 0, and then divide by 2, x is 0. So this is not a no solution kind of problem. This is actually a solution problem. Okay, and then, whoops, second. And now at this point, we're looking at problems that don't have the same base. So ideally, we're creating the same base. And what we want to do is we want to change this base into 4 to the something power. Only because this is 4 to the something power. We know that this is divisible by 2 and could potentially go all the way down to 2 to the whatever power. But now that I know that this is 4 to the 5th, I can go in and compare this 4 to the 5th and 4 to the 2x plus 11. So now that I have the same base, my bases will kind of cancel each other out. And I'm going to be left with this multi-step equation, two-step equation, and I can solve that, okay? So I'm left with 2x is negative 6, divide by 2, x is negative 3. At this point, it would probably be a good idea to go in and check this. So I'm going to have negative 3 times 2 is negative 6. Negative 2 plus 11 is 5. So that works out. It checks out, no problem. Same business with this. Again, I know that 512 can go down all the way to 2, but I also know that 512 is actually 8 to the third. So I'm going to have the same business. I'm going to have the same base. And I can go in and say 3 minus 2x is actually equal to 3. I can, whoops, not add, subtract 3 from both sides. Negative 2x is 0. Divide by negative 2, x is 0. and then we're going to call it good. Same thing with this, 256 is 4 to the fourth. So now that I have the same base, again, it's really nice to know your perfect squares, cubes to the fourth, fifth, sixth, whatever power. If you don't know that, you are going to have to kind of like do a factor tree and come up with the right numbers in order to put it into the equation. Oh, I think my pen. Oh, here we go. It's working. So once you get to this place, it should be fairly simple when you're an Algebra 1 student to go in and see like, hey, this is how I solved it. Again, same thing. I don't know that 343 is 49 to the whatever power, but I do know that 343 is 7 to the third, and that 49 is 7 to the second. So what I'm going to do is I'm going to make this 7 to the second to the x minus 2 power equals 7 to the third. And then when I see an exponent to an exponent, this kind of goes in and does this multiplication bit. And so I'm going to distribute. So I'm going to end up with 2x minus 4 equals 3. I'm going to add 4, so that equals 7, and then divide by 2. And that is 7 over 2. And again, I can leave it improper, no problem. Same thing here. I'm going to turn this 36 into 6 to the second. I'm going to put this as an exponent to an exponent equals 6 to the 5x power. I'm going to end up with 2 times 6x minus 1 equals 5x. So 12x minus 2, that's a weird 2, equals 5x. I'm going to subtract 12x, end up with negative 2 equals negative 7x. Divide by negative 7, x is 2 over 7. We can go in and check these. And honestly, it would just be putting in the numbers into the variable and evaluating. Just like we did with this other one over here. You could check it in your mind. You could check it on paper. It really just does depend what your teacher wants, what your teacher says. I do want to say one thing, that when you have a problem like this, you could just go in and change this as 9 to the second, right, to the 3x. I have seen in some cases, and I don't know that it's an absolute necessity, but to change both of them. So to make it in the most basic base, so the most like I don't want to say like a prime factor because not all of these numbers are going to be prime, but the most the smallest base, I guess, if you will. So you could turn this into 3 to the second to the x minus 4 power and 3 to the fourth to the 3x power, but I feel like that's going to give you more work to do. I did see this in the past, and I don't know that I'm a fan. Sorry, I'm going to just go in and push do not disturb for a little while. Okay, so I'm going to go ahead and erase this because we don't want to do this kind of problem. So now I have this as 9 to the x minus 4. So I've got x minus 4 equals 6x minus x on both sides. Negative 4 equals 5x. Divide by 5. X is negative 4 over 5. Ta-da! We've got it. Okay. 64 is 8 to the second. And 512 is 8 to the third. To the third? To the third, yeah. And then to the x power, and then I've got 2 times x plus 1, and then 3 times x. So 2x plus 2. Again, this is the easy part. We just need to know that how to change the bases to the same thing. Once you know it's the same thing, you're good to go. Because a lot of this stuff is just middle school math, solving these equations. Okay. Same with this 36. 6 to the 2x equals 6 to the second. to the 2x plus 1 power, and then I've got 2x equals 4x plus 2 because I've just distributed. I'm going to subtract 4x from both sides. Negative 2x equals 2. And divide by negative 2. Oh my gosh, this flu is really kicking my booty. Okay. So now we're in these kinds of problems where we've got fractions, okay? So when we have a fraction, assumably we know that 1 over 7 is the same thing as 7 to the negative 1 power, so the x, right? 2,400 is 1, and 1 is 7 to the 4th power. So we can now combine this exponent and this exponent now that we know that we have a base of 7 for both of them, right? So we're at negative x equals 4, divide by negative 1, x is negative 4. Ta-da. Okay. 512 is, I know it's 8 to the 3rd. I think it's going to be 2 to the 9th, but it's going to be 2 to the negative 9th. And I actually don't need a fraction or parentheses because 512, let's take a look. Let's factor this out. So I know that it's going to be 8, 8, 8. And then yes, so I'm going to have 3 2s, right, for each 8. And so I'm going to have a total of 9 2s. And then because it's in the denominator, I'm going to put negative. And then that's going to equal 3x minus 1. So negative 9 equals, whoops, not negative, whoops, equals 3x minus 1 plus 1 plus 1 on both sides. This is going to be gross, but it's okay. Divide by 3, x equals negative 8 over 3. So disgusting, but oh well. Okay. I know that 25 is 25 squared is 625. So I'm going to turn this into 25 to the negative, whoops, to the negative 2nd power to the x plus 1 power, so that I get the same thing on this side where it's going to be 25 to the 2nd minus, or I guess to the 2 minus 2x power. One thing that you'll notice is that this is going to be 25 to the negative 2x minus 2. And this, I could actually rearrange this exponent, negative 2x plus 2. Now, I want to have a conversation about this because this is actually pretty important to notice. These two, and you've done this in the past, these two are really, really similar. And if we were to graph y equals negative 2x plus 2 and y equals negative 2x minus 2, we would notice that they're both parallel. We would know that they're both negative slopes with different y-intercepts, okay? So because they'll never meet, because they'll never touch, what's going to happen is that there's actually going to be no solution, right? Because they're never going to touch. Now, in this case, if I were to set these two equal to each other, I would add the two x's to both sides, and I would be able to cross them out, and I'd have 2 equals negative 2. Now, because that's a false statement, this problem has no solution. The reason why I brought this up is because in the next problem, this is kind of an important thing. What happens when you solve the two problems with different bases or bases that don't quite have the same exact like minimum base, right? So like I know that 9 is 3 to the 2nd, but I also know that 3 to the any sort of power will never equal negative 9. Like that's not a thing, right? And because that's the case, what happens is we're going to actually go in and separate this into one equation, 3 like that. And then we're going to put this equation as a separate equation of y equals negative 9. One of the things that you'll notice when you graph, and actually the instructions for the last actually starting with this problem for the next 6 problems, say to use a graphing calculator to solve the equation. Um, what you'll notice is that y equals -9 will be down there. Let's use blue. So let's say here's -9. And then this is going to, well, that's a terrible line, but okay, we're going to make pretend like that's actually good. And then the red graph, 3 to the x plus 3 power. So 3 to the x is going to go like this, and then it'll go like this. And we know that it's going to kind of like shift over 3 units this way. So actually, if I go in and take this and move it over 3, like 1, 2, 3, excuse me, it'll kind of look like that. So we will see that there is no solution here, but the graph itself needs to be a part of the solution. So you will be graphing these problems, okay? In this particular case, so I have this here. So 1/4 to the negative x minus 1 power is actually 4 to the -1 to the negative x minus 1 power. And then I can distribute this. So I'd actually have 4 to the x plus 1 power, and that would be my y. And then when I graph it, so when I graph that, I know that they're all going to kind of go up like that. And because this is like the base of like whatever the base is to the x power, it'll just get shifted over 1 that way. So whereas this one shifts over 3 this way because I'm adding 3, the other one will shift over only 1 because I'm adding only 1. And then the other piece is going to be y equals 18. So let's call this 18. And then this will be, that's a terrible graph. Let's just bring you up here. And then it'll hit right here. Now, on a graphing calculator, you'll actually see these points. But in this case, in our case, we know that the y is going to be 18 and the x will be whatever it is. Again, these types of problems, you'll learn how to solve them in a different way in Algebra 2. Same business for this one. We're going to go y equals 3 to the x. And when we graph that, let me change colors. Let's make a, so 3 to the x is kind of, well, that's a little bit too not great. It's going to go down, 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 and then up exponentially. And then the other equation is going to be y equals negative. Whoops, I kind of wanted blue. Y equals negative 2x, negative x plus 1. One thing that we're going to know is that this negative means it's going to reflect on the x-axis, and this negative means it's going to reflect on the y-axis. So instead of going like this, it's going to go like this, and then like that. So this will be my final image. Because we're reflecting on both x and y. And because we're doing +1 in the exponent, we're actually going to move it 1 over. So we're going to kind of go like that. And again, in this case, it is, again, no solution. Move these things here. So this will be no solution as well. And we know that because we know that 3 to the anything power will never equal -2 to the anything power. Because how do I put this nicely? In a when you're multiplying a positive number multiple times, that could give you a positive answer only. When you're multiplying a negative number multiple times, that could give you negative or positive. But there's never any situation where a positive number multiplied so many times will give you a negative number. And we see that in this first and third graph on this page. So I've got the same situation here. I'm going to go y equals 2 to the x plus 2. I'm going to have y equals 5x minus 3, or 5 to the x minus 3 power. And then we're going to graph them. And then in this case, I don't have a graphing calculator like up here, but we're going to have a graph that kind of looks like this, and a graph that kind of looks like this. And technically, these two should never meet. They will get super close to each other, but because one of them is shifted to in the left direction, right? So whatever graph this is originally, I'm going to go 2 this way, and whatever graph this is, I'm going to go 3 this way. And these are just graphing transformations. So they're never going to touch. And when you go as far left as humanly possible to like negative infinity almost, you'll see that the graph, and you zoom in really like a lot, you'll see that the graph will never touch the x-axis. It'll just get super close to the x-axis. So this is kind of like where we are right now. I'm going to go with this one has no solution right away. And the same thing is going to happen with this one also. Again, because there's no positive number that will give me a negative base that I multiply. Like if I do 7 times 7 times 7, like however many times, um, it'll never give me a negative number. So I'm going to say that this is no solution. But if I were to graph these, I would probably say we have 7 to the negative x plus 1. And that's going to be a reflection on the y-axis. And then this one is going to be a reflection on the x-axis. So when I do graph them, I'm going to end up with like this kind of, and like that kind of. So you'll see that they'll never meet. So this is a linear function. This should be y equals 1/4 x plus 1. And then this would be y equals 2/3 to the 2x minus 1 power. And then when I graph these two, I'll notice that I'll have one that's linear. So it'll be like 1/4. So kind of like that, where this is 1, you know? Well, okay, we don't need that. And then the other one will be, so 2/3, anytime I have a fraction base, I know that my base is going to go kind of, sorry, not my base. When my base is a fraction, I know that the red graph is going to look like the fraction graph, because this is actually 7 to the negative 1 power. So it's like 1/7, you know? And then this 2x minus 1. So I'm going to end up kind of in this shape, and they will eventually touch. I don't think it'll be this close to the x and y axis, but they will touch at one point. And so they will have some sort of solution. Again, you need a graphing calculator for it. I don't have graph paper or graphing calculator on my screen right now showing, so I can't solve it, but you should be able to with a graphing calculator. You could also use Desmos. Desmos is a nice option. And then this is the last problem. So we know that anytime you have, what do we want to say? Anytime you have a not graphing, but anytime you have a word problem that requires you to use a interest savings, right? So we know that our general formula is my final amount, like my A, is going to be the principal times 1 plus whatever the interest is, right? Whatever the percentage is. So my rate over my how often is it compounded. So the amount of times that it's compounded. And sometimes these letters change depending on who your teacher is or what book you're using, but generally the same thing. And then the exponent will be your your how many times it's been compounded times the time. So in this particular case, my final amount, and we know that we want this account to have a balance of 1,500. So that's my final amount, right? This is kind of important information here. So I'm going to say my final amount should be 1,500. My initial principal is 1,000 because I've just deposited that much. And then I'm saying it's 1 plus 0.05 over it's compounded yearly. So I guess yearly is just one. Sometimes it's compounded quarterly. I think my head cold or my flu or whatever it is making an issue with my reading. I thought it said compounded quarterly. So if it would be compounded quarterly, that would mean it's compounded 4 times a year. We would just do 4 here. But annually is just once. So we could go in and we can say 1 plus 0.05 to the t power, right? And so we want to make sure that we get this um, in exponential form. And this n kind of shows me how often it's compounded as well. Okay, and then it just so this is answer A. Answer B would be when we actually go in and solve it. And in order to solve it, I'm gonna, oh, where's my color? I'm gonna go ahead and I'm gonna divide by 1,000 in both cases. So 1,500 divided by 1,000 is gonna be, I'm gonna move the decimal over 3. So 1.5 equals 1.0, oh, sorry, 1.05 to the t power. I would use a graphing calculator for this. I would go in and say, okay, y is equal to 1.5 and y is equal to 1.05 to the x power or t power. When you're putting it in Desmos in the graphing calculator, you do need to put in x and y. So wherever these two will meet, that will be what time, how long it will take for your account to hit $1,500. Again, I don't have a graphing calculator like shown on my screen, so I won't give that to you, but you can easily go in and it'll show you kind of like where they meet. So your graph will kind of look like this and then like this, and then they should meet at some point in this positive section here. I hope that this was helpful, and then let me know if you have any other questions. I'll see you in another video. Bye.